Okay, now to further understand your concept about your pulleys then and your land core, let's have a sample problem here. Here we have a 100 kilogram block, and A is shown on the image below, and it's released from rest. So here it's being released from point C here, at rest. If the masses of the pulleys and the cord are neglected, determine the speed at the 20 kilogram block at point B in time equals to 2 seconds. So here. So just like what we've shown earlier, it seems that although almost identical show with our example earlier, it's not quite exact. The positions with respect to the datum line will change. For example, SAE here, as soon as the 100 kilogram block is dropped, the length here will vary. So as the length in block B as well in SB. So basically, with respect to the datum line. So first things first is, of course, we build our FBD. So you can start it anywhere. You can start at point B. You can start at this particular datum line between C and B. You can start at point C. The book, however, started out with point C, which would look something like this. So if we were to stop there, that's practically it. But to further elaborate, so from here, we can also add from the block. This is gonna be 2T, and this is A. So we have weight A. Now from the other side, we have a point B. So here's the pulley. So we have here T. We know there's also T here, and in between here, that will be your T, which is equal, and your block B, and this is your weight B. And from there, you can now establish your equations of motion since we're technically finding the speed of the 20 kilogram block point B. That should give you clue as to which equations you should be setting up first. So here is the first one. Notice the signs. So the convention that the book is using is quite opposite to the one we're using. So if we're gonna follow our convention here. This will be negative and this will be positive. This will be negative and this will be positive. So this will be our equation 1. This will be our equation 2. And with that, we can now set up our kinematics equation for setting up the total length of the cord, or just the cable length here. In this case, this is gonna be, so which one are the constant? This is constant length. This is constant length. This is constant length. The one that is not constant is this one, and this one. So that will be SA, that will be 2SA plus SB equal to your total cord length. So in which case, our kinematic equation will yield something like this one. So differentiating it twice, we now have the relationship between the displacement and your acceleration, yielding 2AA equals to negative AB. This will be your equation 3. Now, all you have to do lang here is solve them simultaneously, which we will try to do. So let me just switch my color lang dito. Something else. Let's go for black. So we're gonna solve it simultaneously. Solve it simultaneously. Okay. So in this case, I just using equation 3. So I just gonna rewrite AB into negative 2A sub A, and this one I will substitute to equation 2. So that would look like something like this. That will be negative 29.80665 plus T equals equals negative 40 A sub A And that would equal, rearranging this equation, we can have A sub A equals to negative 29.0665 over negative 40 plus T. Now, this one, we now substitute to equation 1. You simply give it a shortcut. So that's going to be negative 100 times 9.80665. It's going to be negative 980.665 plus 2t equals actually let's not do that. Let's keep the 100. It's gonna be negative 109.0665. That will be 100. And this is gonna be the equation. So negative is gonna be 29.0665 divided by 40 minus t over 40. So divide both sides by 1 over 100, you will have negative 9.0665 plus 2t over 100. And this will be so this will be 9.0665 over 2 minus t over 40. And then you isolate them to get t. So you will have t here, which is 2 over 100 plus 1 over 40. Equals to 9.0665 plus 9.80665. And t should be equal to two hundred 140. There we go. So our t here is going on. Our t here is 3 to 6.8889 newtons. So substituting that to our equations 1 and 2, we will get the accelerations of A is equals to, so that's going to be negative 100 times 9.80665 plus 2 times 3 to 6.889 divided by 100. In this particular case, it's going to be negative 3.26. 26889 meters per second squared. And then A sub B would be 326.8889 minus 20 times 9.0665 divided by 20. It's gonna be positive 6.5378 meters per second. Now, The only reason this is negative and this is positive is because I use a different convention than the one being used in the book. So knowing this now, we can still get our velocity at point B, where we have, it's going to be VF it's going to be VF VI plus A at point B T. So we have time in 2 seconds. We have VI, which is at 0. So simply change that. So we have 0 plus 6.53 meters per second squared times time at 2 seconds. So we have times 2. Your velocity should be still positive 13. What is going on? Your velocity here should be equal to 13.0756 meters per second, or V is equals to 13.08. So in traditional manner, we still have to box our answer in green, and there you go. I'm gonna take a screenshot of this so that I can just simply replace the one in my slide. There you go. Oh, okay. Now we go back to the presentation. Okay, so that's for sample problem 9. And last sample problem is we have this particular skateboarder. So we have 60 kilograms of skateboarder goes down the circular track. Now, if he starts from rest, then our data here is 0 degrees. So determine the magnitude of the normal reaction the track exerts on him when data is 60 degrees. Neglect his size for calculation. Now, this is a different kind of displacement where instead of in meters, we're shown the difference in position by the change in angle, basically. So hopefully you have to review a bit of your geometry. So this is technically an arc length. Okay, we're trying to determine that. So other than that, the problem's asking what the normal reaction of the shell. So what's the normal forces here? So basically the perpendicular ones. So the first things first is we have to draw first our free body diagram. So we have concern here. We're gonna zoom in here. So it's gonna look like something like this. So here's your man. Here's your axis. So we know that there's a normal acceleration towards that point O, and then there's the tangential acceleration along this ramp. Then, of course, perpendicular to that, there is the normal force or the normal reaction, and of course, the weight of the person. Then, of course, the angle of inclination here, or in this particular case, the angle of displacement. So it's kind of similar to what was shown here. And the next step here is basically we have to set up our equation. We start first our equations of motion. So remember, so this is part of the this is a sample problem for your tangential and normal acceleration. So here we're gonna deal first with the normal side of things. So that's the n-axis, if you call it that way. So our summation of forces sub n is equals to mass times acceleration sub n, where an is basically v squared over the radius of curvature. Luckily, we can see here that the radius of curvature is about 4 meters. So with velocity, I don't think we have the velocity here. So that's something we have to figure out. Okay. But for the summation of force on the n, or the parallel line, so we have n here, and that's gonna be something like ns, that's perpendicular, and of course the weight. So we have to show the direction towards the n. So that's gonna be 60 times 9.8066. On this particular case, 9.81. I haven't changed it. Sine theta. So our equation should look like something like this. That will be equation 1. Now we go for the tangential. So that will be force sub t equals to mass times acceleration sub t. So that will be your tangential acceleration, where it should look like something like this. There we go. And we can simplify the equation further, since we can solve the tangential acceleration here with AT equivalent to 9.80665 cosine theta. Okay. You know what? Let's just change it on the spot. Where is it? Where is my PowerPoint? There we go. So let's just change that on the spot. Let's use 9.8066 kagad instead of 81. Okay, and there we go. And then for the other one, so that's gonna be so 9.8066, and then let's try the other one. So there's gonna be okay, and then 60 times 9.8066 divided by 60 should be equal to 9.8066. There we go. There we go. What happened? So here we go, writing the equations again. There we go. There we go. And then after this, we can now set up our next equation. So we're here to determine the normal reaction. So we first set up the kinematics, and using geometric relations, you know that the total displacement will be the theta times the radius, or in this particular case, we have the radius as 4, so that will be 4 theta. So using this, we can now set up our equation. With our upper limit, with our lower and upper limit is 0 degrees and 60 degrees respectively. And ds here will be starting from rest, so I'm presuming from position 0. But in this particular case, we don't have the total displacement, but we do know we can use another equation, which is this one. VdV equals to ATds. So it's kind of similar with equating them in terms of time. So we can use that particular equation where ds here, we can equate ds into VdV over AT. So in this particular case, we can substitute everything. Or actually, yeah, we can substitute ds with 4d theta. So that will be in terms of theta, and we should get the integral of both equations. So the 0 v, so that will be v squared over 2. Then of course we have where v squared over 2 is essentially the okay, we can get that, and then simplifying further, we can get now the normal reaction as follows, which is 1.53 kilonewtons, simply by using this equation. Okay? So just to finish it up, so that's just to double check. So that's going to be 39.2266. 39.8. 9.80665 Let me just edit that a bit. That's gonna be equation 1, equation 2. Let's just remove this one. So that's gonna be 9.8066 sine offshoot times 4, since that's constant. So that's 39.2264 instead. Yeah, let's use that. There we go. All right. So yeah, let's start that again. And we have this particular slides now. I guess this is the updated. So we will equate this now. Yeah, there we go. 1.53 kilonewtons. All you have to do is, thank you, 39.2264. That's sine plus times sine 60 degrees times 2, and then square root that. Actually, you don't need to square root it, since v squared is 67.942 here, which you can substitute to your equation 1. So you can divide it by the radius of curvature at 4 meters times 60. And then plus 60 times 9.8066 sine, I'm guessing sine at 60 degrees. So I'm going to put it that way. It's 1528.6976 newtons, or in this case, 1.53 kilonewtons. Yeah. So that's the other shortcut here. So bear in mind, this is not the, it didn't went from here to 1.53 kilonewtons. So what happened here is that what happened here, wait, let me just choose a different color. There we go, red. What happened here is that, so you'll be able to get the v squared here, which is around, I can just backtrack my calculations. It's around 67.9421. I believe this is in metric, so that's going to be meters in second, which you can then substitute on the equation here, and you will be able to get this one. So you have to get the normal reaction at when theta is at 60. So this one is at 60 degrees. And then you will get around the answer of 1528.6977 newtons, or simply put, around 1.53. There we go, kilonewtons. Okay. Hopefully that's not very confusing, but you can still revisit this at your own pace. And there you go. So again, this is the book. And if you have any questions, we can go ahead up in our face-to-face class. Thank you so much.